morning. Morning. Can we start now? Okay. Well, once again, good morning for everybody. I will continue the topic of Galois theory, which has been started from yesterday by Peter. I hope you will get more detailed information about technically how to compute something here, especially how to obtain extension field here. So as outlined, I make a range. We will talk about a little bit refresh about some notions in algebraic extensions, splitting fields, and automorphism groups, and also finite Galois theory. If time is not enough, so I will stop, and we can continue the next lecture. Now about the preliminary notions here about the definition of extension field, we can see the fact. I know you all already know about the fact in familiar fields. For example, I try to use this blackboard. We know some fields in the number system. We have R as a real field, and we know that this is contain a Q, for example, these rational fields, and also C, the complex. Can you see this? Oh, okay. Yeah. Okay. This is new. Yeah, this content here. Okay. This content here. Yeah. So you know, in some fields, maybe it will be contain another fields like this. C is containing R, R containing Q. So this fact is normal in the field. So we have the notion of extension field of some field F, for example, and we denote it as over F. This is the notion of extension field. It means K is extension field of F, right? And also, yeah, a little bit algebraic structure here. We know that K, the field itself is a vector space, and in this situation we can consider that this K is vector space over F itself. So in this situation we can get the dimension of K over F, and we denote it by this one. Mean dimension of K over F as vector space. So everybody know about this, I think, yeah. Okay, if we have a ring in general, or in this case a field, we can construct a polynomial ring. So from this field F, we can with Fx. This is the set of polynomial over F, and we denoted by, for example, a0 plus a1x plus a2x squared and so on. And in the end, we get the highest power here, n, as a degree of this polynomial. And we define root of Fx as, you can see here, gamma is called the root of this polynomial if it satisfies this one. So when we replace this x with gamma, it equal to 0. So we call it a root. And this is some properties that f a field and let p a polynomial over f is irreducible polynomial, then there always exists a field K containing an isomorphic copy of F in which P has a root. This is a fact here. So the idea is follow. So F field, and we consider polynomial in this Fx irreducible, yeah, this irreducible. Then there exists K. This is F. This is K, containing an isomorphic copy of F. So we can consider F as a subfield of K, because K containing like a copy of F here, in which Px has a root. So if we have Px in a polynomial over F, this is not necessarily has a root in F itself. But if we extend a little bit, maybe it will have a root. But there is always exists this K. Yeah. So this is the proposition mean. Okay, now the definition of algebraic. The element alpha in K is said to be algebraic over F if alpha is root of some polynomial in Fx. So you know that this is K bigger than F. K bigger than F. This is K. This is F. If we put alpha and we find the polynomial P such that alpha is the root of this P, so we call it algebraic. Yeah, this is the meaning of the definition of algebraic. So this you still remember the definition of extension. So if we have the situation like this, we call this K is extension Ff. If all of the element of K is algebraic, then we call K algebraic extension of F. This is the simple example. We know Q, and we can observe polynomial x squared plus 1. And you know that in Q itself, this polynomial doesn't have root, but if we extend with C, it is a root. The root is I, or square of minus 1. Yeah. So this is I is algebraic over Q. Algebraic over Q. Because we find Fx such that this is the root of this polynomial. Okay, the existence of this polynomial actually may be more than one. Maybe it's possible, but we can find the minimal polynomial. It is unique and also irreducible. So this proposition guarantees this situation, and the proof is a little bit not very hard. The proof is easy to prove the existence. It is unique, monic, and irreducible polynomial. And we call this polynomial because it is unique, so we can call it, we can give the special name, we call it minimal polynomial. The polynomial, this is the notation to remember that this polynomial belongs to alpha, yeah. So M alpha F. If it is not necessary, so F, you can reduce this F. So M alpha X is called the minimal polynomial for alpha over F. So the degree of polynomial is called the degree of alpha. Yeah. This is the simple example also. We have, we consider now square 2. This is not in Q. So we have the field is Q, and we take the polynomial in Qx, then this is x squared minus 2. This is in Qx. Yeah. And what is the roots? The roots here is square root 2. This is yeah, this is the minimal polynomial of this one. Yeah, this is alpha. So you know, because this is the order, the degree of polynomial is 2, so the degree of alpha is also 2. Yeah, this is according to the definition. Oh, you also have the second example. This is this is third root of 2. Yeah, third of 2. Yeah, this is also as alpha. The degree is 3 because the polynomial here is x cube minus 2. Yeah. This is the example. I think you already know this proposition. This notion is the same with this one. So this one, which this is an ideal generated by Px. Yeah. So if you have the ring polynomial fx, you factor by this ideal generated by Px, where Px is irreducible, then it will be a field, and we call it, or we notion it by f of alpha. This is the field generated by alpha over f. Yeah, this will be isomorphic, and in particular, the dimension is equal to degree of this alpha. Yeah. The element alpha is algebraic over f if and only if f alpha over f is finite. This is a necessary and special condition when you will characterize an element algebraic or not. You can see from this proposition. So if it is finite, then this is algebraic over f. So moreover, if the extension k over f is finite, then it is algebraic. This is a good condition. Now, how about if we have more than more than 2 fields here? We have 3 fields, f, k, and l. Then you remember this is the notion of the dimension. This one. Dimension. If you have, this is f, contained in k, contained in l, of course this is extension field of f, and this l is also extension field of k, so we can compute this dimension, and also this, we get this one, and moreover l is also a extension of f. So we have also the dimension L over f, and we have the good relation.
So the extension K of f and the extension L of K are all finite because it is not finite.
Yes, you're right. Yeah. In this case, we always think this is a finite extension. Thank you very much. Yeah. This is also true only for finite. For infinite, I don't know, maybe the other situation, yeah. Yeah, this is infinite situation, finite case. This dimension is actually the multiplication of this one, right? Yeah. Yeah, the corollary is clear, yeah, I think. Okay, this is the example. We now consider 6 square 2 as alpha, and the dimension is 6. We have this situation, this one. Q is the Q square, Q root 2, Q square root 2, I'm sorry, I'm still confused with this notation here. Q square 2 is containing Q. It means this is extension field of Q. And this one is extension field of this one. So the dimension is 6. And moreover, we also have this situation. This is the order, the dimension is 2, dimension is 3. And you can see that this is the multiplication of both of these dimensions. Okay, why we have this 6 here? Now consider this alpha, we call it alpha. Alpha is this one. Yeah. So if we cube this alpha, we can get square root 2. So how can you compute this situation? It means we have a polynomial in Q square root 2. Yeah, we have this polynomial x cubed minus this in this one, right? This is the minimum polynomial and this is the root. So this is, yeah, so this one is, no, this is in, sorry, this is in Q square root 2 this minimal polynomial, and you see this is degree 3. So we have that Q yeah. It's 3. Yeah, this is 3. So the dimension of this is the field, extension field of this one, and the dimension is 3 because the minimal polynomial is degree 3. Yeah. So we have this one, this 3, and it means this one. Yeah. And as you already know, this one has a dimension 2. So together from here to here, the dimension is, the order or dimension is 6. So this is the reason. Yeah. Yeah, this is another example. Now we have extension field which have two generators, square root 3 and square root 2. This generate this field over Q, and this polynomial x square minus 3 is irreducible in Q square root 2. You know the degree is 2, so it means the order or the dimension of this is 2. Yeah. So this dimension is 4 because 2 times 2 is equal to 4. Yeah. Okay, now about the composite of two subfields. If we have K1 and K2 subfield of K, we can make a composite here denoted by K1, K2. You can see the notation. It means the small subfield of K containing both K1 and K2. Yeah, this is the example. Consider now Q square root 2 and Q third square root 2. This is two fields, and consider now this 6 square 2 has polynomial minimal both in this one and this one. You know which minimal polynomial? I think like this, yeah. Yeah, this is the minimal polynomial in this field, and the other minimal polynomial you can find it. This is in this one, and what about in the other field? You can make this cube, yeah. Maybe if you this one, right? That means the polynomial is square. That's right? Yeah. This is Q right. Okay. This is degree or order is 2. Yeah. This one, and I mean this alpha is contained in this one, and conversely, any field which contain square 2 and third square 2 always contain 6 square 2 also. Yeah. Hence, we conclude that this composite is equal to Q 6 square 2, 6 square root 2. Okay, now we come to the definition of splitting field for the polynomial in fx. It means if we have fx, polynomial in fx, and fx factors completely into linear factors in kx, and fx doesn't factor completely into linear factors over any proper subfield of k containing f. So I will show you the maybe more easier to understand what is the definition. This is f, and this is k. Oh. Yeah, this is extension field of f, and we have fx here. Now, fx, what is the meaning factors completely into linear factor in kx? Means this fx can be factor to linear, but it is in kx. Yeah, you know kx here. For example, x minus alpha 1, alpha 2, and so on. Alpha k, for example, this is in kx, but fx doesn't factor completely in the field which contain f. So between f and k, if there is another field A, for example, E, for example, this fx is not factors completely in this one, in this ax. Yeah. This means the splitting field. So this k is splitting field for this fx. Yeah, if there is another field, so it could not be happen here. So, yeah. Okay, so some examples I have here. Yeah, I start from the easy one. Consider this polynomial square, this one. This is in over Q, sorry, this is over Q. This minimal polynomial, this one, is over Q, and this extension field is Q this one. Yeah, this is splitting field of this polynomial over Q, because you know that, yeah, I will make the diagram here. Yes, we know that Q is contained in this field, but you know that there is still another field between this one and this one, right? So this Q here and Q, yeah. You know which field in this one, in between? Yeah, and this is also contained in this, yeah? Because this square root 3 is not contained in this one, yeah. And also we have this one, yeah, right. And this field also contained in this one, because this square root 2 is not contained in this field, yeah. So this is extension of this one, and still another field, maybe. Yeah. Yeah, this is 6, yeah. This one. So this polynomial, this is factors completely in this field, but not in this one, or this one. So this is the splitting field of this polynomial. I think I hope you understand the meaning now, yeah. Now I have another example. Is it's a little bit more complicated, because one of the root you already can guess now. What is the one of the root this one? Third, Yeah, this is one of the root of this polynomial, but it is the irrational over Q, I mean. But actually, there are also another roots of this polynomial who involve the imaginary complex number. So the other root are call it beta. Beta, this one times minus 1, yeah, and also gamma. Minus I, yeah, there are 3 roots. So consider the splitting field. So we call it K, for example. Yeah, to make it simple, yeah, we call it splitting field is K, generated by alpha, beta, and gamma. But what happened here? Field, then it contains alpha, beta, and gamma, and also this is the operation between them. Yeah, and we can, this is non-zero, so this is also non-zero. We can make this beta alpha. Yeah. It means this one divided by this one. So the rest is only in this part, yeah. And it means this is minus 1. Yeah. So you know that this field should contain this part. This field also should contain this one, this alpha. So this alpha and this one, square root of minus 3, should contain in K. Yeah, so far you understand, I hope. So this K should contain these 2 elements, and alpha, beta, and gamma, it is enough to produce this one. So if K contains these 2 elements, this one, and this one should be in K also. So this is the generator of this field. Yeah, that means this K itself is okay, now we can continue the dimension or the order of this width of extension. This field is the field of extension field of this one, Q. Here is 2. And also we have Q third square 3, and this field, this extended field of Q, this is the dimension is 6. Yeah? So we have together here so it is the splitting field of this polynomial. Yeah. Okay, this is more information about the relationship between degree of the polynomial and the root. Yeah, if you know the degree is n, then this polynomial should at most n roots in f, and if it is precisely n roots in f, means fx split completely in fx. You already know this situation. Okay, this is the theorem for any field f. If you you put some polynomial in fx, then there is an extension k of f, which is a splitting field of fx. So the splitting field is always exists, and this is unique up to isomorphism. Now this is the general situation in a splitting field. Maybe you may find the same roots. Alpha 1 not appear only once, but maybe 2 times or 3 times or more. This is no problem in this splitting field. Yeah, but we have another restriction condition after that. We call it separable. Separable means this multiplicities should be 1. So you know what is the meaning of this? This means alpha 1 appears more than 1. So the multiplicities show that how many times how many alpha 1 you have in this polynomial. Where alpha 1 and alpha k are distinct, and this ni more or greater or same 1 for all I. So alpha I is called a multiple root if this ni more greater than 1. For example, means this alpha this is multiple root here, because this is 3 not 1. Yeah, this is what I said before. So a polynomial is called separable if it has no multiple roots. So the multiplicities are 1, all 1 here. For example, this is separable, and this is different with the other case. For example, you see this is 1 and this is greater than 1. This a simple example is x squared minus 2. This is separable because only have 2 distinct roots, square 2 and minus square 2. minus root square root 2 square. Yeah, but you know the other case. This is inseparable. This is inseparable. It's clear, yeah. Because we also have another example of inseparable polynomial. Now consider x square minus t over, this is a field, this is characteristic 2, for example 0, 1, for example, yeah. This is polynomial in over this field, this is characteristic 2, and let square root t is root of this polynomial, yeah, the root of this polynomial. But we have another situation here. What happened with this? Yeah, we have x square minus times x times this and times t. Yeah, this is normally square, and we have, because this is order, this is characteristic 2, means this one is 0, the remainder is 0, and the rest is x square plus t. But you know, in this field, this polynomial is also equal to, this minus 1 is equal to 1, yeah, plus 1, so this is equal to, yeah, this is it. So when it is 0, is also this 0. Yeah. So this polynomial have roots, factorized, this is multiplicity 2. It means not separable or inseparable. Yeah, this is for any over field of characteristic 2. You always have this polynomial inseparable. Yeah, it is the proposition said that we can make a little bit tool, yeah, to see what is if fx is separable or not. We can use the derivative here. Derivative means not derivative in calculus, but the idea is the same, but not by limit. Suppose this polynomial suppose this polynomial, what means the derivative is dx of fx we define as this is A1. This is this is like a normally derivative, yeah. But we define it not by limit but by definition, yeah. And the proposition said that fx is separable if and only if this polynomial and this derivative is relative prime. Yeah. So we can see in this example. For example, we have polynomial x to p to n minus x over fp. You know, fp is with characteristic p prime, yeah, and has derivative this. This is the derivative of this one. We use the definition, yeah? And because it has characteristic p, means this is 0, and you always have this equal to minus 1. What is the meaning? It means the polynomial has no roots, yeah, has no roots. So the polynomial has no multiple roots, hence it is separable. Yeah. This is the, oh, I think, I'm sorry, this is the wrong example. Yeah, this is the wrong, I'm sorry. Because this should be P, maybe F2, this is true, yeah. Again, this is polynomial, special polynomial, x to n minus 1 has derivative nx to n minus 1. Over any field of characteristic not dividing n, this polynomial has only the root 0, which is not a root of x to n minus 1. So the polynomial is also separable, and they have n distinct root of unit. Yeah. This is the application of this definition and proposition. I think, yeah, still 1 or 2 minutes. Yeah, this is the other proposition, the other properties. Every irreducible polynomial over a field of characteristic 0 always separable. You know, in our example, more of them are over Q, so Q is characteristic 0, so most of them separable. Yeah? A polynomial over such a field is separable. Irreducible polynomials, and also every irreducible polynomial over a finite field F is separable. Polynomial in Fx is separable if and only if it is the product of distinct reducible polynomial in Fx. Yeah, I think to make us comfortable from one part to another part, maybe I should stop now, because in next lecture, and I think in Friday, we can continue to what is the Galois theory is. So this is such an introduction to Galois. But as the next lecture, we will talk about automorphism of K. So this extension of it, we can produce what's this isomorphism between K itself. And we collect them, we call it automorphism of K. And this is a tool to learn, to study about Galois theory. Okay, thank you very much. I should stop now. Thank you.